In this lecture, we will focus on the concept of the derivative. So we introduced it in the previous lecture, and now we will build on it substantially. And so recall, this was the key slide from the previous lecture. So the derivative of the function f of x at the point x naught is given by the limit of this difference quotient. And we may not have actually named that before, but that's what we call this. This is our difference quotient. Now, this, recall, the difference quotient itself can be thought of as two different things. One, this is the slope of the secant line connecting the points. We had drawn it before. This was x naught, and here was x naught plus h, and here was f of x naught, and up here was f of x naught plus h. Then our secant line the slope of this secant line was nothing more than this difference quotient because it represents the rise over the run of that line. When we took a limit, the secant line became the tangent line to our graph. So this secant line snapped into the tangent line. And the key there was to take the limit as that h term went to 0. So as this h term went to 0, this interval here shrunk down to a width of 0, making this point migrate along the function to this left-hand point, and in the process, that secant line snaps into the tangent line when we actually take that limit. So this slope of the secant line becomes the slope of the tangent line when we introduce the limit. That's point 1. Point 2, remember that this represents the average rate of change of the function f over the interval x naught to x naught plus h. When we let the width of this interval shrink to 0, the average rate of change becomes the instantaneous rate of change. Now this was defined at the specific point x0, but we could just say any x could be plugged in here. And that's in fact how we define the derivative of the function in general. This definition is the derivative of this function at the point x0. Our more general version will be replacing x0 with a generic x, and that gives us the formal definition of derivative. The derivative of the function f of x is the function. Notice that the derivative, if it exists, will be a function. F prime of x, defined by the limit as h goes to 0 of our difference quotient, provided that the limit does exist. And we have the same interpretations. F prime of x is going to be it gives you the slope of the tangent line to the graph of y equals f of x at x. And it's also the instantaneous rate of change of f of x with respect to x at x. And it's a key thing to note here that this derivative, if it exists, gives us a new function. For some terminology, the process of computing a derivative is called differentiation. And if f has a derivative at a point x naught, we say it's differentiable at x naught. If a function is differentiable at every point of its domain, we say the function is differentiable. So let's see this in action. Suppose we're given this function x squared plus f of x equals x squared plus 3, and we want to find the tangent line to this curve at x equals 2. So the first thing we need to do is calculate this derivative. And so we have the limit as h goes to 0 of f of x plus h minus f of x over h. And we plug x plus h into the function. So f of x plus h, we just replace this x with x plus h. We have x plus h squared plus 3. So that's our first term in the numerator. Then we subtract f of x, which is x squared plus 3, all over h. And we simplify and then evaluate the limit. For those of you who have seen calculus before, if you are asked to compute a derivative directly from the definition, this is the way you have to proceed. And I only mention that for people who have seen calculus, because if you have seen calculus, you know some quicker ways to do this. We'll learn those soon. But when asked to do a derivative calculation directly from the definition, this is the method. And you want to be very careful when you do this. Always be writing your limits. So let's FOIL out this term. We'll get x squared plus 2xh plus h squared. Plus 3. And then distributing the minus sign, we'll have minus x squared minus 3. All over h. And you'll see that some terms here cancel. The x squared and the minus x squared cancel. The 3 and the minus 3 cancel. And we're left with 2xh plus h squared all over h. We can cancel one of those h terms. So we get the limit as h goes to 0 of 2x. So here we have an h canceling, and here we'll have 1h left in the numerator. So we have 2x plus h. When we evaluate this limit, this h goes to 0, and so we get an answer of 2x. So this tells us that the derivative f prime of x equals 2x. So at any point x, the slope of the tangent line is given by 2x. In our example, we are asked to find the tangent line when x equals 2. And maybe we should draw some things here to see what this looks like. So x squared plus 3 we know is the graph y equals x squared shifted up 3 units. So this is our f of x. We can also graph our derivative. Remember, derivative here, it's a function. This is just the line y equals 2x. So we will go here and then rise over run up 2 over 1. And the way to understand the relationship between these two functions is that if you pick any point on this graph, say you pick a point over here, the slope of the tangent line at that point, to get that slope, you simply go down and pick the value off of, the corresponding value off of the derivative. And note, I should have written, this is f prime of x here. So this blue graph is the graph of the derivative. So again, at any point on the black curve, if you want the slope of the tangent line, you go to the corresponding point with the same x value on the blue curve, on the derivative. So the question we were asked is to find the tangent line at x equals 2. So maybe we'll draw that in orange. So we are here at x equals 2. And so this is our tangent line. And we know the slope of our tangent line. We use x equals 2. We plug that into the derivative. So the slope is going to be f prime of 2, which we see here is 2 times 2, or 4. And then, of course, for a line, we need a point on the line. Why not just choose f of 2? So our point would be 2f of 2. And of course, f of 2 is 2 squared, 4, plus 3, or 7. And then our tangent line becomes y minus the y value, y minus y naught. So y minus 7 equals the slope 4 times x minus x naught, which in this case was 2. And so this gives us the slope of the tangent line, which I didn't draw very well. It actually, maybe we can get in here and redraw it. So our tangent line is at the point 2, 7. So up here, and we have a slope. That wasn't very good either. So there's our tangent line. And we have a slope of 4. So again, the point here is 2, 7, and the slope is 4. So this answers the question, but it's important to recognize, again, that this derivative at any point on the function, if you want the slope of the tangent line, you need only go down to the derivative value at the same x. And you can see it in this picture. So note that starting here at x equals 0, this line intersects the origin. The derivative is 0. So f of 0 is 0. But notice here, the slope of the tangent line is horizontal, which is 0. As x gets bigger and bigger, linearly, the derivative is moving into positive territory, which means steeper and steeper tangent lines. If we go left, so if we have x go from 0 towards negative infinity, f prime of x is getting more and more negative, which means our tangent line slopes are getting more and more negative. So you can see how this line, this graph of the derivative of f, tells us a story about the slope of the tangent line to this black curve, y equals f of x. So this is a very common type of question. Oftentimes, it's very standard in differential calculus courses to expect students to have an understanding and a mastery of this type of question. Let's do another one. So suppose we are asked to calculate the derivative of this function. And these questions tend to be a little bit more involved, and you have to be ready to use your algebra skills and be careful with your algebra skills when you do these. So when you see these, you always start out with the definition. So we have f prime of x equals the limit as h goes to 0 of the difference quotient, f of x plus h minus f of x all over h. And then we plug in to the function, limit as h goes to 0. So again, replace every instance of x here with x plus h for this first term in the numerator. So this becomes x plus h over x plus h minus 1. Then for our minus f of x term, we just subtract f of x itself. All divided by h. And then we work through the details to simplify this difference quotient and then evaluate the limit. So we have the limit as h goes to 0. Oftentimes I prefer, instead of dividing by h, we can multiply this numerator by 1 over h. So we have 1 over h times. And what we need to do here is get a common denominator. So the common denominator will be the product of these two denominators. So we're going to take that first term, x plus h over x plus h minus 1, and multiply it by x minus 1 over x minus 1. And then this second term we need to multiply by the other denominator, x plus h minus 1, over x plus h minus 1. And this will then allow us to combine the terms. So we want to FOIL this numerator out. So we have the limit as h goes to 0 of 1 over h. For this first term, for the first, we get x squared. For the outer, minus x. For the inner, plus hx. And for the last, minus h. Multiply this x through, we get x squared plus hx minus x. All over our new denominator, which is x plus h minus 1 times x minus 1. Now, we simplify, and we see that we have an x squared and a minus x squared. We have an x and a minus minus x. And we have a plus hx and a minus hx. So a lot of things cancel. And this reduces us to the limit as h goes to 0 of, we still have this 1 over h hanging out front. And in the top, the only term that survived was a minus h. And then we have that same denominator, x plus h minus 1 times x minus 1. And now we see the h's cancel. So what remains is the limit as h goes to 0 of negative 1 over the quantity x plus h minus 1 times x minus 1. And now we can apply our limit laws. So we would first apply the quotient law, limit of the top over the limit of the bottom. And then in the denominator, we would apply the multiplication law. And then we would apply the sum law. And remember, that is what we often refer to as direct evaluation, this h dropping to 0. And what we have left is minus 1 over the quantity x minus 1 squared. And this gives us the derivative of this function. So again, these are very standard types of questions. You see them homework and on exams. And you want to be very comfortable doing these. And the key to these is to take your time, write them slowly. This is also the type of problem where you have to be doing some bookkeeping. You have to be very carefully writing all your terms, keeping track of things, and doing careful algebra. Very important skill to have when you're doing math. Those of you who study more calculus will see even more of that as you go further. That being said, there are some different ways to denote the derivative. This is just notation, and they all mean the same thing. Well, you might look at this and think, why do we need all these different versions of a name for a derivative? F prime of x, y prime, dy dx, df dx, the derivative of f of x with respect to x. Also here, derivative with respect to x of f of x. And the answer is, depending on the context you're working in, you will have one of these being most appropriate. And in first year calculus, we use all of these. So in different contexts, some of these are more appropriate than others. And so you'll see that used quite a bit. And you'll see the notation makes sense. This is probably the strangest looking notation, given what we've studied so far. These others make sense. F prime of x was the name we gave it. If y equals f of x, then you can think of y prime. It's like putting a prime on both sides. Here, this is saying, you can read this as differentiate with respect to x, the function f of x. Same thing here. Take the derivative with respect to x of f of x. These we call differential notation. And really, when you think about the history of calculus, it was Newton who used this kind of notation and Leibniz who used this. So as the two scientists, mathematicians, developed the theory completely separately from one another, they had different notation. So to talk about the idea of differential notation a bit, we can revisit the picture, the tangent line picture that we had before. So remember, we had this picture where we said, we'll be a little bit more succinct here. Suppose you're at the point P there, and then you're at the point Q here. Well, this difference we would call delta x, the change in x as we move from P to Q. And then over here, on the vertical axis, we would call that distance delta y. And remember that the slope, so again, we usually have a function here going through these points. And then we had said that the slope of the secant line so the slope of that secant line was just rise over run. So we looked at that geometry when we developed this idea of derivative. But then we wanted the slope of the tangent line. And so our tangent line for this graph would look something like this. And the slope of the tangent line is a result of taking a limit. So the limit, and I didn't draw this tangent line terribly well. Let's try that again. A little better. But the slope of that tangent line came from taking a limit of this rise over run term, letting delta x shrink to 0, which remember had this Q point migrate down to P, and then that secant line snapped into place of the tangent line. And the differential notation is using this idea where the slope of the tangent line, why don't we call it m, it's the limit as delta x goes to 0 of that difference quotient delta y over delta x. And that notation we use is dy dx. So you can think of this as, here's your average rate of change, the slope of this secant line, delta y over delta x, or rise over run. But as you let delta x shrink to 0, and that secant line snaps into being a tangent line, we take this limit, and so you can think of it as that delta y over delta x change from these sizable intervals to these infinitesimal intervals, which gives you this idea of instantaneous rate of change. So that's where this differential notation comes from. It's from this picture. So we're going to get into more detail here on derivatives in the next lecture. But it's important to remember that this lecture and the previous one give us the real bare bones of what's going on in differential calculus with this idea of instantaneous rate of change and slope of tangent lines. This is the underlying principle of everything in differential calculus.